Okay, so today we are doing our last lecture for kinetics. What I want to do first is take a look at these diagrams in front of you. They're actually not the best diagrams. The first problem on this is that this dotted line right here is representing activation energy. So we'll say it's about 120 here. It should be in the exact same spot here. So we're going to say this is also 120. So looking at these pictures, what this is an example of is how temperature affects rates of reactions. And this is, rather than just saying as temperature increases, reaction rate increases because molecules have more energy, this is just a physical or a pictorial representation of that. So underneath each of these curves are molecules, and it's the same number of molecules under this curve as under this one, so it would probably be better if this were a little bit bigger. But regardless, ultimately what happens, if you take a look at this diagram on the left, at 300 Kelvin, this particular system still has an activation energy at 120, but only the molecules in the shaded area have enough energy to actually react. Have enough energy. You can see that when the temperature then increases to 400, the entire curve shifts left and more molecules have enough energy. So all this is showing is that when temperature changes, your activation energy is the same, but more molecules are capable of reacting because they have met the requirement of having enough energy, which is the activation energy. So this is just a pictorial representation of that. Looking at the next picture, this is a little bit better. This is describing what happens when you add a catalyst. This is an uncatalyzed reaction up here. We can see that our activation energy is here, which looks to me like it's greater than 120. So I'll just write energy of activation greater than 120 joules. I don't know the unit on that, it could be kilojoules, but it's energy. Well, here if we add a catalyst, what happens? The activation energy lowers. Comparatively, the uncatalyzed reaction only has this many molecules that are capable of reacting, while the catalyzed lowered the activation energy, so more molecules now meet the energy requirement for reacting. Again, just another representation in picture of how to describe something. So if you ever get lost for words, you can use these diagrams to describe both how temperature and how adding a catalyst affect the rate of a reaction. So now let's move on. On this picture is another quick review. We did this on the first day of this unit, but again, just want to make sure you understand these energy profiles. Energy of reactants, energy of products. Important that you know how to find delta H from the picture. Activation energy is always the energy from the reactant to the tippy top where the activated complex is. So please be familiar with these. You can expect to see them again, hint, hint, cough, cough. Now, what's new for today? Today, we're introducing something called the Arrhenius equation. Arrhenius, A-R-R-E-H-N-I-U-S. Okay. You will be utilizing this equation to find activation energy. That's the whole point. We have never up to this point have calculated the activation energy. You've just talked about it. But now you're actually going to get the opportunity to calculate it. This is the Prelab question is based on a graph. And on your AP equation sheet, you will have the following version of the above equation. It's a linearized version, and that equation looks as follows. Natural log of K is equal to the negative activation energy over R times 1 over T plus ln of A. ln of A is what has to do with the orientation of the molecule, which I'll talk about on the next slide. but you never really utilize that. But I want you to realize, this being on the AP equation sheet, if you're asked to graph to find activation energy, like we've been doing with Clausius-Clapeyron and other incidences, you're going to utilize this linearized version. To get activation energy, you're going to put the natural log of your K's on the Y and your reciprocal of temperatures on the left, on the X. This should look really, really, really familiar, because when you were doing this before, it was natural log of pressure, right? So that was Clausius-Clapeyron. This Arrhenius is super similar. And again, your slope of this line after you graph it is going to equal to negative activation energy over R. So to find the activation energy, you're going to go ahead and multiply by R. Just like with heat of vaporization, you cannot have a negative activation energy. Remember, activation energy is the energy needed to put in, so that's going to be a positive value. So make sure when you solve, you end up with a positive activation energy. So this is the pre-lab question number 1. Why is there a relationship between K's and temperature? Well, let's just think about it. As temperature increases, we know that reactions speed up, right? Well, if you think about a rate law, if we're not changing concentrations and the reaction's speeding up, then the K must be changing. So K's are dependent on temperature. K's in kinetics. All right, rate constants are temperature dependent. So when you're solving for activation energy, there's 2 things you can do. You can use this linearized equation on the AP equation sheet and actually graph a bunch of points like you do in the pre-lab, or if you're just given 2 data points, you can plug it into this equation, and like we did with Clausius-Clapeyron, plug in your 2 K's, plug in your 2 temperatures, and solve for the activation energy. Okay? Pretty much the same thing that we've been doing with Clausius-Clapeyron. Collision theory, we've talked about this. I do want you to know that there are 2 requirements for reactions to happen. And this is the unlinearized version. This is where those 2 equations on the previous page came from. They were derived from this equation. But ultimately, the 2 factors affecting whether or not, or determining whether or not a reaction can happen, is if the molecules collide, first of all, with enough energy, and that's what the EA represents. And the molecules also have to hit at the right orientation. This is an orientation factor. You never have to do math with it. It's just that A gets higher and higher and higher the more complex the reaction is, and the more complex the collisions have to be in order for the reaction to happen. Okay? So those are the 2 factors. Collision at the appropriate orientation and collide with sufficient energy. If I were to ask you a question, I would ask, what would my question be? My question would be, what 2 things must happen for a reaction to occur? Molecules must, 1, collide with enough energy, and 2, collide at the appropriate orientation. And if you want to pull this equation out of your hat and look like you're an awesome, brilliant student, you can do so. If not, I'm okay with you just using words in that scenario. Okay, let's practice a couple problems. These are just like the ones we've done in the past. Hopefully I'm not making any math errors. I'm sure some of you will come and tell me tomorrow that I messed up. But looking at this problem, it's asking for calculating the activation energy. So I notice I have 2 points. I have 2 temperatures and I have 2 constants. So I'm going to use that double Arrhenius equation. First thing though, let's go ahead and write down my couple pairs. My first pair is 300 degrees Celsius, and I've got a K of 2.41 times 10 to the negative 10th. Now one thing you need to do, and a lot of you miss this on the test, you need to convert that to Kelvin. Okay? On the last AP test, a lot of you did not convert your Celsius to Kelvin when you did your Clausius-Clapeyron, and your heat of vaporization was wrong because of it, so be super careful there. If you write the units of your R, you will see that happening. 400 degrees Celsius in Kelvin, that's 673, And the K they gave us in the problem above is 1.16 times 10 to the negative 6. Our job is to find energy of activation. So I'll write my unsubstituted equation first, and I'm going to do the double one. If I'm going too fast, this is a video, you can stop it, slow down at any time. And then T2 minus T1. Okay, so all I'm going to do is plug and chug. I'm going to use my first couple, natural log, my K1 is 2.41 times 10 to the negative 10th divided by K2 of 1.16 times 10 to the negative 6 is equal to, I'm solving for E of A, plugging in 8.31 joules per mole K, solving 1 over T2 minus 1 over T1. Okay, when I do this math here, I end up with negative 8.48 for the natural log quotient is E of A over 8.31 times, and when I do my little fractions there, I get negative 2.59 times 10 to the negative 4th. So as I continue to solve, I am going to multiply my negative 8.48 by 8.31, and I get negative 40.4688 equal to activation energy times that negative 2.59 times 10 to the negative 4th. And then I'm going to just divide both sides by negative 2.59 times 10 to the negative 4th, and I get E of A equal 227,080. This is going to be based on my R, joules per mole. So to make my life a little bit easier, I'm just going to say 272 kilojoules per mole. Hope I did this right. Y'all check my calcs for me. If I got it wrong, I'll give you a sticker if you come and tell me I got it wrong. How exciting. I'll even give you a superstar sticker. Okay, let's go on to the next problem. If the activation energy for the decomposition of N2O5 is 1.0 times 10 to the second kilojoules per mole, calculate the temperature change necessary to double the rate at room temperature. So we're starting out at a room temp. If you don't know what room temp is, that's going to be 25 degrees Celsius, not unlike my classroom, which is more like 85 degrees Celsius. So that's going to be 298 K. All right. I want to know what temperature is going to be required to double the rate. Okay, well, I don't have anything about K's in here. What do I do? Well, I'm in this little corner, I'm just going to write a little note. Think about rate laws. Rate equals K times A. I don't care what the order is. It doesn't really matter. If I am keeping a constant concentration and I'm asked to double the rate, is it not fair to say I could just double my K? So wouldn't doubling my K double my rate? Yes, it would. So what I'm going to do is just make up some K's, and I'm going to double the K. So I'm going to say, hey, at 298, my K is 1. What temperature do I need to have to double the rate? Well, what's the double of 1? 2. So I'm going to have K is equal to 1 here, and it's equal to 2 in this case, and I want to know what's the temperature change required when I double the rate, what's going to happen. So I'm just going to plug this into my double equation again. And so I get, I'll write it unsubstituted again for you. ln of K1 over K2 is equal to EA 8.31, 1 over T2 minus T1. So if I'm going to double my rate, I'm going to start with a rate of 1 and end up double that. You can put anything in there. If you want to put 5,000 and 10,000, whatever you want to do. Regardless, that ratio is going to be 0.5. Is equal to, they give me the activation energy of 1 times 10 to the, and I'm changing it because that's kilojoules, so I'm going to change it times 10 to the 5th joules. That's an important part right there. watch yourself, divided by 8.314. And then what I'm going to do is multiply by T2 is what I'm looking for. What temperature do I have to get to start from my room temperature T1 of 298? So plugging all this into my calculator, we know this from first order yesterday. This is negative, oops, I think I messed this up. I'm going to pause and fix this. So I had it right. So we're going to take the natural log, and we get negative 0.693 is equal to, when I divide these two numbers, I get 12028. 1 over, I'm solving for that, divided by 298. Okay, when I divide negative 0.693 by 12028, I get negative 5.76 times 10 to the negative 5th is equal to 1 over x minus 1 over 298. I'm going to add 1 over 298 to both sides, and I get 0.003298 is equal to 1 over x. If I inverse that, I get 303. Now, that's not my answer. That's the temperature at which the rate is doubled. But look at what the question's asking. The activation energy is given, and they want to know the temperature change. So if I was originally at 298 and I went to 303, my temperature change is 5 degrees, or just say 5 Kelvin. No degrees. 5 Kelvin is my temperature change. So the rule of thumb is usually as you go up 10 degrees, the rate of a reaction is doubled. I don't know if you guys remember that from Chem 1, but that's very much a rule. It's going to be very much different. It's going to be varied for all sorts of situations depending on strictly the activation energy. So that's it. Hope you guys get it. All right, come see me tomorrow if you have questions.